So likewise for the Brent, you just do that. So we have R petrol 92 and R Brent, and then we have to generate the period variable, which is the you can treat it as a time indexed, which corresponds to the positions of the observations, okay, respectively. And so in order to tell Stata that I want to have this data to be of time series data, what you have to do is you have to apply the TS set on period. So setting this into time series data, and then TS line R petrol 92 and R Brent. The diagram would look a little bit different from the one in class because R petrol 92 and R Brent are different. Okay, the formulas are different. So as you can see that they still retains the wandering pattern, right? Okay, it's just like the drunkard, being away from home, it takes a very long time to come back. So, but what is interesting about these two data is that it's different from where you remember that I generated unit root y and unit root x, and they have nothing to do with each other, and here it is not. Okay, here the two are having the same common stochastic trend. That is to say that the trend, even though the trend is stochastic, what does it mean by stochastic? It's random. Okay, so you can see that there's no clear increasing or decreasing trend. It's just kind of very stochastic trend, but they have a similar trend. Okay, similar stochastic trend. So you may ask, why do they have this? Well, it's because as you pointed out, that they are all related to oil, and also more importantly, and this is more reasonable and explanation for why they have the same common stochastic trend, is that when this one go up, this one also have to go up, this one go down, this one also have to go down, up, up, down, down, right? Why is that so? Well, it's because because otherwise there will be arbitrage. Okay, if the price of one go up and the price of something is just kept constant or going down, then definitely there is arbitrage. And if there is arbitrage, the people will get to know that, and they can buy and sell. So the market mechanism will drive the price, so that the price of the one that is going deviating away from the others would be following the same trend. Okay, so they in the end they should have the same stochastic trend. So that is the context for this question 5, right? So that is question 5b, and we still need to draw the program. Program of R petrol 92, right? So you can see that the autocorrelation is very high, and then it is getting smaller, but it's quite persistent. It lasts until even period 38, and whenever you see this kind of trend, you know that you should suspect that there is a unit root problem. Okay, what else? We need to see the program. Please remember that the program here, the autocorrelation, looks slightly different from what we have in class, because we have different formula now. Okay, so that is what we have, and what can we conclude from the plot is that there is a unit root is wandering, and there's a very persistence in the data. That is also confirming another confirmation that there might be unit root problem here. Okay, but we never know. We have to apply the Dickey-Fuller test on that. So in order to apply the Dickey-Fuller test on that, we have to make sure that we know what is the correct number of legs of the first difference, and here we have our petrol 92. Okay, right, so that gives us the first leg. Okay, instead of 2 it is 1. Okay, so in the class we found out that it is 2. Okay, and Vasok that is, these are not socks. Okay, Vasok brand. Okay, you also have the leg 1, right? So that means that we are going to use leg 1 for the liquid fuller test, for the augmented liquid fuller test. So the fuller, okay, the fuller on the R petrol 92 with the leg 1. Yeah, I'm not too familiar with the stator. I'm more familiar with R. That's why I kind of get confused when you have leg S and when you don't have S. It turns out that I think it is the same, right? So if you have that, then this is the test statistic that you have. So you can see that it's quite different from the one that you have in class, where it was like -1 point something, and it shows clearly that, you know, there is a unit root problem. But however, here you can see that this one is quite big, right? And if you draw the liquid fuller, then you can see that. Let me get the color. Or do I have the color? Okay, then the values that you have is around here, and this value 2.8 something is for 5%, right? So you can see that you are rejecting at the 5% confidence interval. However, for this 1% critical values, it is still bigger than that, right? So that means that you cannot reject. Okay, if it is you cannot reject if it is 1%. So the 1% is somewhere here. That means that it is still on the right of this blue one. That means that you well, you can treat it as a unit root at a very strict critical value, 1%, right? So I think just treat it as having a unit root, okay? Because we kind of confirm it through the diagram. We kind of confirm it through this program here, and this is still on the margins of rejecting. Okay, so therefore we just treat it as having a unit root. So let's move on to talk about the R brand. Also leg 1, right? For this one is much better, right? You can even reject it with a more flexible, more easy critical value. So therefore you can say that this one, for the R brand, it is very likely that there is a unit root. Okay, so yeah, so just treat that these two have the unit root. Okay, so let's move on to question D. Right, so in order to do question D, well, you can run the NUI, okay, of the Y, which is the R petrol 92, onto the R brand. Okay, and the legs here is, you just take the leg 5. Okay, so where do I get this leg 5? Okay, so leg 5 is taken from the M here, where we don't take all the T, we just include up to M. So how do we get the M? The rule of thumb is that we take 0.5 times with T with the power 1/3. Okay, and our data set is it has about 200 plus, and that is almost the 200 with the cube root would be roughly equal to 6. So 0.75 times with 6 is 4.5. So you have to round it up to 5. Okay, we don't take 4. We don't round down, round up. Okay, So here we have the new on the y on the x with a leg 5. Okay, so you might ask where is it in the note? Okay, where is it similar to the note? It is actually, let me put it out for you. It's actually similar to this one. Okay, where you just regress y onto x. And what happened is that because ut might have the might be serially correlated, so we have to use this method, okay, the HAC, to adjust for the variance of beta 1. Otherwise it is not efficient. Okay, and in order to adjust for the variance of beta 1 hat, we have to times with this. The original OLS just have this, we don't have this FT. Okay, so again, the M is there. Instead of taking the whole T, all the time series, all the observations, we just use M. Okay, that is the rule of thumb. Okay, so we use that. Okay, instead of regression, instead of this, we just use mu e to denote that, okay, it's the OLS, but please adjust for the coefficients, the estimate of the coefficients variance. So here you see that the coefficient should be the same with the OLS, but the standard error is different. Okay, and you can see that now is positive. All right. So next we have to check for the whether there is a co-integration. So that is under this. All right. So how do you check for the co-integration? Okay, that would be in the lecture 16. Sorry, the lecture 16, where you have this part here, where you have the testing for co-integration. All right. So what you have to do is to use the ADF test on the residuals. Okay, why on the residuals? Because if you might have the residual to be having the unit root, okay, as I shown in the class earlier. And remember that if x and y are kind of okay, let me get it again. Okay, remember this. Okay, let me hold on. Remember this one, when I generate the y and z data using over here y and z data, and then I take the first difference, or even if when you take the y then minus some constant times with z, okay, you take that difference, okay, you see that the difference between so the difference between y t minus any constant of zt, okay, if you have this and this to be unit roots, but they are not co-integrated, then the problem with this is that the result of this, okay, would be, let's say that we call it vt. Okay, we've just constructed new time series data out of this one. This vt would have the unit root. Okay, you can see from here, okay, even though this is just y minus z, but you can generalize that to the case of y minus something times with z. You will see that the red here, you see that there's a unit root. So if they are co-integrated, okay, then we don't have this problem. We don't have this problem, which is this is unit root. And that is why we have to check to see whether this one is equal to 0. And if this one is equal to 0, that means that the u, okay, the variance here is having unit root problem. Okay, and if it is a unit root problem, then your data is something like that. Okay, but we know that our data is not the case. It's not like this. It is like that. that means that they have the same stochastic trend. Over here they don't have, the blue and the green doesn't have the stochastic trend. Okay, so therefore we just test for that, and in order to do that, well, you have to take out the, where is my data? Okay, you have to take out the residual, but of course the residual is not inside here. It is not yet a variable, so therefore you have to create a residual variable out of the residual. Okay, you might wonder why do you have to use a predict, because predict here is that you use your data to generate the receipt. Okay, and that is the residual. So I want to call from within the model that I want the residual to be out from my estimation here, and based on the data that I have. Okay, so you predict, so you see here that the receipt is created, and that gives you the residual. So with this receipt, and please note that this receipt is like the U hat, okay, the U hat that you have. So let's run the VASOP to see receipt. Okay. And you should not have any lag, because AIC tells us that lag is the optimal lag is equal to 0. So therefore it's good. You just have to run the defuller, okay, on the receipt. Okay, and then the number of lag is equal to 0. Alright, and okay, when you run that, this is what you get. There's no lag, and the t-statistic is minus 3.24. Okay, and that is in between here. So what do you say? Whether there is a unit root? Well, here you have to be careful. This is the decufuller, but we are using not the decufuller, right? Actually, according to the note here, you are using the ADF, right? So it's a angle ranger ADF. So where's that? Okay, it's here. And for the number of x in the equation, so it's 1. That is this. Okay, it is in between here. All right. So that means that you can, well, in this case you can reject at the 10% level. It is quite loose, okay, but well, just think of it as no unit root problem. Okay, you can reject at 10% level. If that is the case, you can reject, and you can say that, well, there is no, it's not a spurious regression, but it is a co-integrated. Okay, so the Petro, what's that? Petro 92 and R brands are co-integrated. Okay, because it has this stochastic trend, common stochastic trend. Alright, so that is part B. Alright, so let's jump into part E. In part E, what you do is you just you truncate the data, condition it onto the year being greater than 2005. So you can use this Petro 92 brand. Okay, running y on x if year is bigger or equal than 2005, lag is 4. Okay, Okay, how do you know its length is 4? You just take 0.75 times with the cube root of this, so that gives you roughly 4. Okay, so this is the regression. So now you do the same thing as part D. We have to create a variable called resid2. Okay, if here, okay, residual. So what you are doing here is that you want to limit only to the year bigger than 2005. Okay, and use this model and the data here, that the data here you control for the year being bigger than 2005, and generate the residual, which is a predict. Okay, so the residual here is means that it is a U-hat generated out of the model, and store this residuals onto the or U-hat here onto the resid2. Okay, so you can run that, and then you see that there's a 60 missing value generated because of you just want to truncate the year to be more than 2005. So now you have to do this before you run the Bigfuller test on that. Resid2. Okay, please remember D, because you want to see the how many first different legs you want to include, and the optimal value of legs is 0. So then you can use the Bigfuller. Okay, resid2. So it is 0 legs, so you just run that. So what you get here is this value. Okay, and you can see that this value is very much bigger than just now. Just now you get 2 minus 3.24. Right, so this value is bigger than this value, and therefore you have more evidence to say that our petrol 92 and our Brent are co-integrated. Okay, you see that 3.42 is somewhere here. So that means that you can reject the unit root in the residual at the 5% level. That means that if that is the case, this means that the what's this? Where's that? Sorry. This means that okay, that means that you can reject H0 and say that this is smaller than 0, and there's no so instead of no co-integration, there is a co-integration. Okay, so that is part E. Okay. Yeah, so that's it for question 5.